Okay, let's start.
Okay, ladies and gentlemen, before I start, you have submitted your first lab report. There are smart people looking at your lab report. Do not give the same report. I was told by the instructors when I asked that some of the reports were identical, so they gave it back. Why did you do that? It should not be right. Give it to you, they bring it to me, I cut it, and I put 0, and you have to do the lab again. That's the rule. Right? So they bought me about 6 of them up to now. After I told them that they should not give it back and change, because you should not give the same thing. And don't also give the same thing by changing it a little. Like some people have written, some people have done the equations like this way, the calculation, and the other party has taken the same calculation and written it this way. Sometimes English, if they look the same, if this, basically the idea is the same, but you are written in different English, we know you have taken it from somewhere, right? Copy. So we said 0, I put copy on it, put a big circle on the places that we feel your copy, and I said I wrote down and signed, say that you have to repeat the lab. Which means you have to repeat the lab. The entire lab you have to come again on some other day, and you have to redo the lab. You keep doing this, you are in trouble. Right? So please don't do that. Do your own work. Right? Okay.
I thought I'll give you a heads up because apparently some of you have done things and they have handed it back to you. I specifically asked them not to do that. They take it from you, give 0 and hand it back to you. Right? And then also once you get your mark 0, the next mark that you're going to get would like not be more than 45%. It's a C. When you give, and I think somebody has put on the net also saying that this is like a school where if you don't come to a lab session, you have to provide the medical report and all that stuff because we are so strict, like a school. You ask yourself the question, why is it like a school? It's because you simply act like your school kids. So if you act like school kids, we treat you like school kids. Right? So you don't come to anything, you arbitrarily come to during some other session. No university will actually accept this kind of thing. But I have been in all parts of the world in other universities, they don't accept this kind of thing. You just walk in one time, I want to do the lab now. If this kind of thing happened in the US, I would have said, get out. You can't do this. Right? And all over the world also, these people also pay money to come and do this work. So we don't want to hassle ourselves. So please be careful, right? Especially with the ones that you're taking with me. There are rules and there are rules. There are another rules also. Okay. Not a good way to start the lecture, but anyway, at least, So I want to do a couple of problems before I start on this. Hopefully I can identify Here you are. Is it the same thing? 529272. Okay, that's it. Okay, let's do this question. Because I want to go back and try to do a little piece of what I stopped. We were doing, I guess, nodal analysis, and we will use nodal analysis on this and show you how it's done. Okay. Right. So let's try applying the nodal analysis to this question and see how it works. Whatever the type of of course you realize that if you look at this question, you have a 9 ohms resistor and a 9 ohm and a right? You can see, though it doesn't look like it, this 9 ohm and 7 ohm resistors are parallel, right? So you can add them. Those things you can do, but of course, remember, if I ask you not to do that, then of course you shouldn't, right? I mean, if somebody gave me this problem, I would have taken these two resistors and added them together. These two, of course I can't. So these two are added. I would have made the circuit look actually more easier to handle. So let's look at this. Get this out. Black. So you realize this and this whole area is the same, right? So that will constitute a single node. You realize from you have an element here, those two meet, that's a node, right? You realize this branch and that branch meet, so that makes this a node. Of course, this also is a node, but we, as we said the other day, we will ignore that. And this whole thing, what you have here in the bottom, is a node, right? So now that is the first step in identifying what are the nodes in the system. Then you mark them so you can identify them. This is 1, this is 2, this is 3, and this one, is node 0. So if you mark this as 1, V1 is the node voltage. Now we don't look at anything else, we just start applying the rule. So basically here is the rule. If this is A, that is B, and if you have the current that is flowing like this, and if this is R, you have a rule that says VA minus VB, and over R is what is I. Right? Pretty straightforward. Use that rule in all the situations that you have faced. Now here, if I start from here, I take this node. Now since we are applying the Kirchhoff current law, we need a surface around the node. Now of course you don't have to draw the surface around the node when you are doing an examination, right? I mean, if you draw this straight line here indicating this is your node, that's enough. But because we are, starting out and in fact learning, we would write this, right? I mean, you don't have to do it all the time. So you realize this particular current is going out of the surface. This is going. We will assume this is going out of the surface. We'll assume this also going out of the surface. So we will say. So of course here is a node, and then here is the other surface for the second node, and this would be the surface for the node 3. So we will start to write the equations. We apply the Kirchhoff current law to the first node. So this goes out. Oh, sorry. So you apply it to the first node. So this goes out. You got that 5, and we are simply going to assume that this also goes out of the node. So that is plus V1 take away 0. We know that this node voltage is 0 over 2, which is this resistance. Then what we have here is we are assuming the current is going to go out. This is plus, so you got V1 take away V2, because this side the voltage is V2, over 2, which is this particular resistance, is equal to 0. That's the first equation. So equation number 2, we apply the Kirchhoff current law to the second node. You have actually 4 links that are exiting this surface. We assume this is going out, so we have V2 minus V1 over 2. See, V2 minus V1 according to this. Plus, we have that, this is V2, this side is 0. So we have V2 minus 0 over 9, right? This is 9. Then over here, we have plus V2 take away 0, V2 take away 0 over the resistor 7, and based on the other side we have V2 take away V3 that over 2 equals to 0 would give me the Kirchhoff current law exiting the second node surface. Okay, so we have that. Now what we have to do is to apply the Kirchhoff law to node 3. 3 is here. You got this, you got this, you got that. So we have V3 minus V2 according to this. V3 minus V2 over 2 means the current is going out of the surface. Here, this we are assuming it's going out of the surface, so that is plus V3 and minus on the other side, it is V0 over 2, that is this particular resistance, plus then over here we understand since this part is earthed, this is a ground voltage, based over here this is equal to 20. And then here this is equal to V3, so V3 take away 20 over 4 equal to 0 is the application of the Kirchhoff. So you got 3 equations. If I want to find V1, V2, V3, I would make sure that all my equations look like, I have to ensure that all of these 3 are taken and my equations look like A11 V1 plus A12 V2 plus A13 and V3 is equal to some I1. Then you have A21 V1 plus A22 V2 plus A32 V3, that equal to I2, some I2 value, I don't know, this once you do this you will get it. Then A31 V1 plus A32 V2 plus A33 V3 is equal to I3. So you have to convert these 3 equations into that form. Now it is in a sort of a matrix form. You can apply the Raymonds rule to find the answers. Right? So it's very straightforward. Right? Completely straightforward way of handling the problem. We use nodal analysis because why? If we have a circuit which looks very parallel, and also we have a lot of current sources in it, preferably we will be using the nodal analysis to solve the problem. Okay? So that is a sort of I guess revision that you are supposed to do. I would also want to do a second problem, which is 8.49. Again, I am doing all these problems from the questions that I gave as tutorial. Right? Even this question is one that I gave in the tutorial. This is actually 8.47. Right, 8.47 in your set of problems. I would also want to do 8.49. Let's see whether we can identify 8.49 here. This one, right? 2 amperes, 4, 2, 4, 6, 10, 24. This one. Cut, select, take a screenshot. Okay. We are supposed to use nodal analysis on this, right? So if I ask you to do this using nodal analysis, tell me how you would solve this. What would be your steps? What would be your strategy to ensure that the problem can be solved easily? Yes, what would you do? Would you just go ahead and start putting all the nodes and putting down the equations? Or would you come up with a different sort of plan to handle the problem?
Okay, first of all, why don't you tell me exactly where the nodes are?
Let's start from there. So if somebody asks you to use nodal analysis on this, first thing you do is find out the nodes. So here, this is a node, right? This has an element. This has an element. These two branches meet. So hence, this is a node, right? You realize this is a node, right? There is a branch. There is a branch. Those two branches meet. That's a node, and all the others are okay except this is the ground node. Good. So now you identify the nodes. Now when you start applying this nodal analysis technique to this, what will happen? Yes. Nothing will happen. We will be able to do it. So why don't we do this? Why don't you take it down? Now I have given you the nodes. Write the equation. Okay, I think I got my answers from a couple of people, so we are on the same page. Good. Second person to ask that question. So I'm glad somebody noticed that. Okay, here is the deal. This question, if you don't do anything, just look at the question, jump into it and try doing it, you will realize that when you write the equation for the second node, there is a supernode. Right? Of course, it's not very difficult. The supernode can be put together and then everything can be done. That's no problem. Right? Or, what could you have done? Immediately taken the 24 volt source and the 12 ohm resistor together, done a source transformation. Immediately when you do a source transformation, what will happen? You can do it source transformation. Your problem becomes easier because why? That will be replaced by a current source and a resistor which is going to be parallel. So now your entire circuit looks like what? Completely parallel. You can address it very good. I will just leave this a little bit. I'll go back to the earlier question. Now, if you observe very carefully here, you realize when I wrote down this equation, I have assumed that the current flow through the 2 ohm resistor is going out. V1 take away V2 and over 2 ohms. See, that's what I have here. Okay, that's what I have over here. But when I come to the second node, I am assuming the current is going that way. I'm assuming it's going out. Now you have a problem. Now in the previous case I assumed it going out, but in the second case I am assuming it going in the opposite direction. Would that cause a problem? So you realize, if I take this equation, if I assume this current is going up, right? If this current is going up, I will have an equation what? So we will call this current is I1 and this current I2. Okay? Sorry. Let's call this I2. So basically this I2 is going to be what? I2 is going to be VB take away VA, right? Over R. VB take away VA over R. But if we assume that this one is going in the opposite direction, you realize I2 is minus I1, which still is true. So let's say, for example, so it doesn't matter, right, which way you assume, as long as you use the same convention to put down the equation. So we'll take, for example, hopefully I can move some of these things up and down. Okay, let's move this up a little bit and let's make it a little smaller, right? And let's get some space in here. Ooh, not good. Let's take this whole thing. I can't move it anywhere. I'll make it smaller, right? Okay. Now I have a little space here. We will assume that this current is still going to go like that. Let's assume that. Now in the second one I have assumed it going opposite direction. Without that, we'll assume that it is going out of this node 1 and still assume when I go to node 2 it is still going out of node 1. Let's put down the equation. If I run the KCL for the node 2, I will have a what? This current is going in. So I should have minus of, since it's going from here to here, I have to take V1 take away V2 and over 2. Right? It's correct, because why? This is going into the surface. I have assumed going out of the surface to be plus. Okay? So plus I would have V2 take away 0 over 9, right? Then plus V2 take away 0 over 7 and V2 take away V3 over 2 equals 0. Now you tell me whether there is any difference between these two equations. That's no difference. Right? So if you are interested, you can assume one direction, right, for all the currents that are flowing in the network. Write the equations, but appropriately you have to make sure the plus and minus come into it. So equations are not going to be any different. Not different at all. Right? Now, did I answer the question? Go home and think about this. Yes? Answer the question. Right? But remember, this is what I use. I don't care where it's going, how it's coming out, or where it's going. I know if I take VB, take away VA over R, it's going from B to A. If I take if I take the equation to be V
A minus B over, I know it has to go from A to B. Then when I take the actual equation into account and I put the algebra into place, I need to figure out whether it's going into the surface or on the surface. That's up to us. Right? Okay? Everybody?
Right. Now let's look at this one. Let's say we did not look at it. We were asked to do it the same way without any kind of simplification. I just go into it without looking at the problem very much and I start doing it. So this is node 1, node 1, node 2, node 3, and this is node 0, and I start to put down my equations. How do I put down my equation? That is going to be the surface for node 1. This is going to be the surface for node 2. This is going to be the surface for node 3, and I am going to write down my equation for surface 1. This is going into the surface, but I have assumed going out of the surface to be plus. So this is minus 2. So I say KCl to node 1. This is going in. I am assuming going out to be plus. So this is minus. Then this should be plus. V1 take away 0 over 6. That's going out. And from here I am going out. I say V1 take away V2 over 10 is equal to 0 is the first equation. Then I apply the KCl to node 2. I apply it here. I will take V2 minus V1 over 10. I am doing this because it makes it easy for me to always take going out of the surface. Right? So I get all these equations that way. Then I have plus V2 take away 0 over 4. Then I realize halfway into it, I can't do it that way. Right? Because I begin to realize that there is this node between 2 and 3, it has only a single voltage source. If there's a single voltage source between two nodes, that will generate something called a supernode, because we are not able to apply the Kirchhoff current law. You can't apply it across this voltage source. So this whole thingy up here will generate a supernode, and we have to write this equation for the entire supernode. So I would say KCl to 2 and 3, which will indicate I am applying it to the supernode. I will get V2 minus V1 over 10. I am considering this, and this one V2 take away 0 over 4. I am considering that. Then I am considering this plus V3 take away 0 over 12 being equal to 0 will be the Kirchhoff current law that is applied to the supernode. And then also we realize if there is a supernode, to that supernode we need to apply what? Kirchhoff voltage law. So V2 take away V3 with Kirchhoff voltage law to 2 and 3. V2 take away V3 should be equal to 24. I got 3 equations and 3 unknowns. So I can use the Cramer's rule to find any of the voltages. Is that okay? Right? That's fine? Okay. So that is the first method. That is the straightforward, without thinking kind of method that you would apply. And the second technique of handling this problem would be to take this 24 volts and the 12 ohms resistor and then convert it into using source transformation. So basically on the other side I have that right? I have that, and this is something like this, because we know this can be switched. Now this is something that you have seen prior to this day. This is 12 ohms. This is 24 volts, and that should be equivalent to a current source going up. Remember, this source direction has to be carefully looked at, because this can go other way, right? So this is 24 over 12 with a resistance of 12 ohms. I can replace it here, and I can still apply the Kirchhoff laws to this. Okay, so let me also quickly do that before I get on to the next section. Right, so maybe I'll take this, Control C, Control V, and yeah, we got it. This is 2 amperes. This is 6, 10, 4. This is 12. That is 2 amperes. Right? So now I can go back and solve the problem again. I would do what? First of all, I have to identify the nodes. This is 1. This whole thing is 1. And this whole thing is the ground node. This is node 1, node 2, node 0. Now I can apply my Kirchhoff voltage law. So, Kirchhoff current law, not the voltage. Now, here you realize I don't have a supernode. Directly I can apply any equation I want. So I will apply the Kirchhoff current law to the first node. I would get this is going into the surface. So it's -2. This I am assuming to go out of the surface, V1 minus 0 over 6. And I am assuming this going out of the surface, which is V1 minus V2 over 10 is equal to 0. And then I take and apply the KCL to node 2. I would obtain, I'm assuming this one is going base out of the surface. So I have V2 minus V1 over this resistance, then V2 take away 0 over 4, that's for this one, and this one I get V2 take away 12 over 4, V2 take away the ground potential over 12, and this also is going to go into the surface, so that makes it -2 is equal to 0. So I got two equations. I got two equations, and I got two things that I don't know. I can apply the Cramer's rule. Right. In the earlier case, I had 3 equations, and I got 3 nodes, and I had to use the Cramer's rule to identify what goes on. Right? Is that okay?
Anything in here I need to explain again? Yes. You are okay? No, not okay. That's the part. Why it goes up? Okay, second one, what happens? Okay, here is what I did. To apply the rule, the KCL, I got a surface, right? And then here to apply the thing, apply the KCL, I have a surface. This current is going into the surface. That makes it -2 because I'm assuming right? I'm assuming ones that are going out to be plus. So this is minus. How about this one? You have a surface. This also goes into the surface, hence minus, right? Any question? Yes. Probably I will be the person who asked, right? And next to you is still learning. Yes, what is it? That's the question. You solved it. You're smart. You solved the question. That's actually yesterday's book. Yeah. Okay. Anybody else? Can I ask any question before I get on to the next one? Because I want to look closely at source transformation. Oh, smart. Yes. Very good. See, that's the kind of interaction I need from you folks. I'll tell you what he said. And hopefully he's understanding it the way I'm trying to explain this. If you look at this, very good. If I look at this, right? If I look at this, now I can rearrange this thing any way I want, right? Nobody said no. Now he says, why can't you do this thing arrangement like that? Is that I have not changed the circuit, why? Have I changed the circuit? No, because in the branch I can flip anything. I told you, sir. Absolutely I can do this. The moment I do this, what happens? Yes, moment I do this, this becomes a node, this becomes a node, this becomes a node. You don't have a supernode. Because why? I can rewrite this as, if this is V1, if this is V2, and this is 24, this is V2 minus 24 over this resistance 12 is the current that is going to flow through this. Go home and try it. You should get the same answer. No supernode. In fact, maybe at examinations I will give questions without indicating which way to use, and if you do something like this, you will definitely get 2 marks. Because you have made the problem very simple. I mean, extremely simple. Now you got only two equations. In the earlier case, you have 3 equations. Good. Excellent. There you go. Pay attention and you get this kind of thing. Thank you. Right. So any questions? Any other questions? Or maybe there's a third different way of, we did 3, fourth way of doing this problem. There is a 5th way also, not to do the problem. Right? Everybody okay? Fine? Let's go to the next one. Now, we were doing this
little bit about, let's say we can extend the source transformation. Let's try to extend this source transformation, understand some additional information about this source transformation. So we sort of said if we have a resistance and a voltage source, right? Resistance and a voltage source, where this was RS and that was VS. This is completely equivalent to a current source, where this is equal to Vs over Rs, and there is a resistance in parallel called Rs. Right? This is what we said. No? This is what we said was the source transformation. I just want to show you that there is a connection between these. We already saw the connection. We saw the equations and all did. But I want to show an additional connection here. Now, if I look at this and if I call this A and B, could you tell me what VAB is? If I look at this one. Yes, VAB is what? Yes, what is VAB? Huh? Why is it minus VS? VS. Right? We understand. This is VS. Right? Because why? This is open. Because it is open, there is no current flow to RS. Hence, no voltage drop. So it's VS. This is in fact called the open circuit voltage. Right? Or we call it also VOC, open circuit voltage. Right? Done. Now here, so basically if I take this and I apply a short circuit to this, let's say I take this and I apply a short circuit to this, there is a current flowing through that branch. Can you tell me what is I? Yes? You don't need to be a rocket scientist to tell me that this is Vs over Rs. Right? Vs over Rs. Now when we take this system and apply a short circuit, we call this the short circuit current in the circuit, short circuit current. Now let me go here. Let me do the same thing. I can find V open circuit to be what? Here, can you tell me the V open circuit? If I keep it open, what would be the voltage VAB? Yes. So this current source going up goes out, and it cannot go out because that is open circuit. It has to go through RS, right? Yes. Now, when I ask question like this, don't look, right? This one goes through that, comes down here. Since this current is going through that, coming down, voltage is going up, and it is equal to what? Vs over Rs and into Rs, which is Vs. What is this? Open circuit voltage. We have kept it open. Then if I apply a short circuit to this, and I call this current I, what is the short circuit current I? Vs over Rs, because Rs will get basically shorted out.
Right? If I have a resistor and I put a short circuit in front of it in parallel, no current is going to go through the resistor because it has an easier path to travel the short circuit. Hence, that resistor will be shorted out, and still I is going to be Vs over Rs, which is what we call I short circuit. So this is in fact called I short circuit. Now then again, if you take now this system, you have an open circuit voltage and a short circuit current. You have like what? You have okay. I am getting a little ahead of myself. Okay, so now we understand these are the same, right? Both circuits are getting the same equation. Now I will say that if I look through this, come out a circuit, look into the circuit, there would be an impedance here. We call that impedance. This is an equivalent impedance. We call it R of TH. We will tell what this TH means. RTH is the resistance or impedance looking into the circuit. Now, basically, R of TH is V open circuit over I short circuit. Now, in your advanced level also, if I want to find out the impedance inside, you did this. I don't know, we did this experiment during our advanced level. We put a short and found the flow, the current, and then we opened and found the voltage. That by that is the impedance. This is a standard equation. The impedance by looking into through base AB. Now, how much is that? We understand in these cases, V open circuit is Vs, and I short circuit is Vs over Rs. It's what? Simply Rs, right? So if I have this source, whichever way I convert it, I look into it, I have a equivalent impedance looking into the system to be Rs. This is the reason why it is called the input impedance of the source, or input resistance of the source, right? Series resistance or the parallel resistance. Now, the case is sometimes we want to analyze the circuit by considering only these input impedances in the circuit. Now, what we are going to head into the next level is to show you that to actually show you that if I want to eliminate this resistor, if I want to eliminate this source from the circuit, what it means is that I have to take out the source from the circuit, but I am going to replace it with its internal impedance or internal resistance. Now, in the section that comes after, we probably will have to remove one circuit. Now, what we mean by saying removing one circuit is to place that source with its internal impedance. Now, if I look at this, right, voltage source, tell me if I want to remove the source, what I should replace it with, so that when I look through this, I have an equivalent impedance of RTH. That's the question that we have to answer. So let's go to the next page. Let's go to the next page, and we will take a look at this and answer that question. Here. So I take this and I want to make sure that this particular source, right, voltage source is eliminated. But I also, when I say it is eliminated, what I really want to say is I am eliminating the source, but I am replacing it with this internal impedance. Now you realize, if I can do that, this is what I want. This is Rs. So when I look through this, I only see the Rs.
No difference, because why? In the earlier case, when I had that particular source, when I looked through it, what was the impedance? Rs. I want to now make sure that I don't have the source, but when I look through it, I still need to get Rs. If I want to do that, for this, to go from here to here, what have I done? I have replaced my voltage source with a, yes, what is it? With a short circuit. See, if I take my source and I replace it with a short circuit, I will get the same output equivalent impedance, Rs. On the same count, if I have a current source, where this is Rs, this is Vs over Rs, right? And I want to look through this and I want to make sure my RTH is equal to Rs. Now, if I have the source in there, if I have the current source in there, I get Rs as my equivalent impedance. I already showed you that in the previous slide. Now I want to eliminate the source and I still want to get the impedance Rs. How can I do that? I can do that if this becomes equivalent to that, where this is Rs, and when I look through this, RTH is still going to be Rs. How can I do that? The only way I can do that is if I actually replace that current source with a open circuit. See, if I place this one with an open circuit, then it is eliminated out of the circuit. When I look through this, I don't have a source, but the impedance is still going to be Rs. Now, this is a fundamental rule that we're going to use with the analysis that we're going to do in the next few minutes. Please remember that voltage source is replaced by a short circuit if I want to place it with its equivalent impedance, and a current source is placed with an open circuit if I want to make sure that the impedance, that the input impedance, that the equivalent impedance still remains the same. Now, with that piece of information, let me go and talk to you regarding the next major sort of technique to do electrical circuit analysis. That is called the superposition. Superposition theorem. Now, this superposition theorem, what it says is that if you have a network of voltage sources and current sources, you can analyze this circuit by considering at any one given instant a single source and replacing all the other sources with their internal resistances. And finally, you is adding up all of the changes and the variables of each individual circuit to find what happens with the complete circuit. So essentially what this says is that if you have a circuit with two voltage sources and we want to find some voltage across a resistance, what it says is don't analyze it using all the sources because it becomes difficult. Mesh analysis, node analysis, all kinds of analysis has to be used. They say that take away all the sources except one. Now, when I take away, what I really do is I want to make sure the system doesn't change. Hence, what I do is I only take away the voltage source or the current source, or the internal impedance still remains in the circuit. So now, if I have two sources, voltage sources, I have two circuits, each one having one source. Easy to analyze. Quickly analyze. Find this voltage across the resistance from the first circuit. Find this voltage across the circuit of that particular resistor in the second circuit. Then, if I put both sources together, that voltage across the resistor is nothing other than the addition that I got by considering only a single source. You can linearly add. So, this is what it says in the superposition theorem. So, let's take an example. Here, this is how you analyze it. Say, for example, you had a circuit with 2 voltage sources. Right? Let's say you have 2 voltage sources. Right? This is E1 plus minus, that is 54 volts. This is R1. This is 24 volts. That is I2, which is the one that we are supposed to find. This is R2 and it is 12 ohms, and this is R3, that is 4 ohms, and this is minus plus, that is E2, and that is 48 volts. Now you realize this one can be easily analyzed using either the nodal analysis, because you know like one node, or you can do this using, I guess, mesh analysis. You will have two loops. But what we are right now trying to do is to take this circuit and apply it to the superposition. When I apply it to the superposition, what it says is that this should be broken down into circuits where each circuit has only one source. Each circuit has only one source. So now here, if I am going to keep that source, I have to eliminate that source. How do I do that? By replacing it with its internal impedance. If it is a voltage source, how do I replace it with its internal impedance? It is by putting a short circuit on it. I just showed you that. See? If I want to have the same internal impedance, I have to take out the source by putting a short circuit so that the circuit remains the same in terms of the equivalent impedance. So, essentially what it's saying is that take this out and you are going to replace it with a short circuit. The moment you replace the short circuit, the input impedance or maybe the internal impedance would come into play. Right? Short circuit. Now, this is what we are trying to find. Now, the moment I take away, I am only getting a part of this variable. So, hence I call it I dash. Now, in the second circuit, what I want to do is I want to keep the other voltage source, eliminate the one here, which means what? I have to replace this with a short circuit. Replace it with a short circuit, and that is called I double dash. So essentially what it says is that if I do this, if I have n number of different sources, I will have how many circuits? I will have n number of circuits with one source, everything else would be resistors. One source with everything else resistors. And then basically what I want to do is I want to find out I2. Now this I2 becomes I2 dash plus I2 double dash. You see? Now your circuit becomes easier to handle, but you have many circuits. Now if somebody asks you to find I2, basically I2 dash, I2 dash, then simply you can do that. Here if somebody asks you to find I2 double dash, I can immediately do that. How do I do it? Now here I can take these two together because these two resistors are going to be in parallel with each other. So this is what 12 times 4 over 16, 3, right? So these two when I combine together, you will get, so if I combine R2 in parallel with R3, you get 3 ohms. Is that correct? Check the algebra, right? So if this is 3 and this is 24, this is 28. Right? Is that correct? Huh? Sorry, 27. So you will have that I being equal to what? 54 over 27, right? Amperes. Now how do I find this current? You know that I2 dash would be equal to capital I into 4 over 4 plus 12. How do I know this? This is the current, right, divider rule. I2 dash is found very easily. See, 2 steps I can find the I2 dash. I do the same thing here. How much is this? 12 into 24, 36. How much is that? 12 into 24 over 36. Right? This is 4. Right? So R1 parallel to R2 is 4 ohms. 4 and 4 would be base 8, and that would be I is what? This capital I would be what? Minus 48 over 4 plus 4 is 8. Is that correct? You mean here? Yes, I didn't quite get it. Which one is 8? R1 parallel to R2 is 8. Yeah, 3 times 8, right? 24. So 8 ohms, 8 plus 4 is 12, right? So how much is this? 4 amperes, right? Minus 4 amperes, right? Now you can find I2 double dash, which is I times 24 over 24 plus 12. I can find I2 dash. If I know these two, I can add it up and find that, right? So, but if you did the problem using mesh analysis and so on, this would have taken a longer time for you to solve, right? Longer time for you to solve. This is super question. If you have current sources, if you are place eliminating, you will substitute with what? An open circuit. If it is like this voltage source, you will have substituted with a short circuit. So here, this is sub-circuit 1. This is sub-circuit 2. Please remember, if you have 3 sources, whatever sources, you have 3 circuits. If you have 4, you have 4 circuits. Each of them have only one source taken at a given time. Superposition means take each one, then add up so that you find the final answer. Now, one of the most common mistakes that students do at examinations, I have no idea why that is, probably most of them are dyslexic, that they take one source, keep everything else. That's not the rule. The rule is keep one and take everything else. Keep a source and take all the other sources out. But at an examination, what you do is you take out a source and keep everything else. Completely opposite to what you are supposed to do. Right? I think here's the reason. This is the reason. The reason is, first year students generally tend to believe the seniors in most cases, and there are some very smart seniors, and there are some seniors who think they are very smart, and there are some seniors who are not smart. Right? So all 3 of those people come and do for you cooking classes. Because why? They want to look good. Right? Yes? You would want to do that too, right? You know, see? And they come and tell you the wrong thing. But they are also learning.
will come and teach you the wrong way. So I see like a massive crowd in the class doing it the wrong way. So I know those are the people who have gone to all the Kukti classes. You know what are Kukti classes, right? Yeah. I guess in the jargon of the university, this is very famous. So you have to be smart. It's like you're doing a research paper based on Wikipedia information. I can go and put anything on the Wikipedia. If you think that that's the true picture of what you're trying to learn, you're wrong. Wikipedia is edited by you. Right? Anybody can edit and put anything in there. So, please be careful. You have to know to learn from somebody else also. Right? You can't say, I have no idea, you tell. Because that's the only way. Please put your phones off. That's the only way that you could have made, such a lot of people could have made the same mistake. Same mistake, all wrong, perfectly wrong and perfectly right in the wrong way. Yeah? Remember, you take a single source, all the others in the network will be replaced by their internal impedance. Okay? Now you are seeing, ladies and gentlemen, things are beginning to rack up very, very, I guess, rapidly. Let's do nine, 10. Oh, by the way, ladies and gentlemen, today there is no break because it is a short duration. I am stopping at 3:30. Yeah, another 45 minutes. Okay, let me do a second example, 9, 10. Oh. You understood this, right? No problem. No, I didn't understand. What part did you understand? You understood? I said, you understand, you throw like this. I'm thinking to myself, I work with international people. Right? They say, in all the other parts of the world, when you say yes, the rule is yes. Right? Then it means no. Very clearly, all parts of the world, no is no. Signal. But in Sri Lanka, there is a so they are not sure just say yes or no. So I told them, no, we are more advanced than them. That is maybe. So they can do it or we can't do it. We don't know, maybe. Because I can't. Okay. So I'm going to do a problem of this when I come back next time. So in the meantime, you should have looked at it and then understood it before I do that. Now the next one is yes. Good. So I'm getting some feedback from the class. So I have told all your first year lecturers to talk to you folks each month so that we get your problems quicker. Okay, his question was, now here this one that I am going to find, this current has to split between this and this, right? Correct, no? 4, 12 plus 4, correct?
Okay, here's the deal there. Okay, let me go there. So if this is I, right? If this is I, and if you have a resistor here R1, you have a resistor here R2. I don't care how it is, as long as these two ends of the resistors are connected together, right? Remember, if the two resistor ends are connected together, I consider it to be basically parallel. So now, if I have I, basically the stuff that goes over here, let's say I1, that is I2. I know I1 is by simply using the rule of the current, right, divider. This I1 is equal to R2 over R1 plus R2. Then I2 is equal to capital I times R1 over R1 plus R2. Okay? That's what I have applied here. See? 4 over 4 plus 12, and then over here I am splitting it between 24 and 12. So base I into 24 is this current over 24 plus 12. Is it okay?
The others also might want to check it. Yeah? No. Okay. What is it?
Let's go to the next one. Now, for some reason, people find this next section very, very difficult to understand. Yeah? But it's not difficult, it's very simple. That's for me to say, right? The next one that we are learning is called the Thevenin and Norton theorems. Now this is going to be our next lab, right? Norton theorem and Thevenin theorem is going to be our next lab. So hopefully if you don't understand it here, you can understand it in the lab, right? Here's what it says, which is a really cool idea. He says, if you take a huge circuit, I don't care what size of circuit, if you extract a load resistor from it, everything else can be replaced by either a voltage source
in series with a resistor, or a current source in parallel with a resistor. Now we already know these two things. Source conversion have those two, right? Isn't that what it is? Basically what it says is, if I have a huge circuit, I don't care what the circuit is, if I can extract from it a load resistor, everything else in the circuit here is equivalent to a single resistor with a voltage source, or it can be equivalent to a current source with a single resistor. That's what he said. Now this rule is the one that we call the Thevenin rule. He said it. I'm sure Norton was running around. He said if he can do it, there is source transformation, this can also be done. So this was stated by Norton. Right? Norton and Thevenin. Maybe somebody else looked at Norton and Thevenin and said that's source transformation. I don't know. Right? Maybe there was a little argument there and then they came on. So essentially what he says that we don't care what the circuit is. To extract this load resistor, everything else can be replaced by a source with a resistance in series, or a current source in parallel with a resistance. Now this is the easy part. Now the difficult part is, how do I find these two? Right? How do I absolutely find? It so happens that this internal resistance RTH that we came across earlier, the TH part came from the Thevenin resistance. Right? RTH. So essentially when they did this, they called this the R of TH, indicating is a Thevenin sort of a resistance. This was known as V of TH, indicating Thevenin voltage. And this was R of TH, and that was called this I short circuit. And it so happens that this R of TH is nothing other than V open circuit over the I short circuit. It's very nice because we have a good explanation of the source conversion over on the other side. Then we did some little jugglery with that source conversion to identify what is the internal resistance. It so happens that that same resistance is what appears over here. Right? Now the question is, how do I find this? Now, of course you can find the RTH using V open circuit, I short circuit. But there's also another way of finding RTH. And the other way of finding RTH you already know. What is the method? Take all the sources and replace them by their internal impedances. What does that mean? All voltage sources, replace them with a short circuit. All of the current sources, replace them with an open circuit. Whatever you have, will only have what now? Only resistors. Now you can combine the resistors using your advanced level knowledge to find a single resistance, and that happens to be RTH. Right? So this is basically a kind of a culmination of all of these stuff that we have learned in this two fundamental theories. I don't know why we find it difficult. I will show you some examples and then you will realize there's nothing bad about it. When you do the experiment also, they will show you all of those things, find the I short circuit, the current and all that stuff. But this is easy because why? Now all of a sudden, I don't have to do analysis, mesh analysis, nodal analysis, no other analysis necessary. I just take the entire circuit, I don't need, replace it with a single source and a resistance. do the rest of the part. So this is a technique of making your circuit analysis easy. Let's take an example and see how all this stuff that I just now told you is implemented. Probably that's the little hard part. So let's look at this. Okay. Hopefully I can locate this. So please read the book because it gives you a little explanation of what these things I just told you about. But this explanation is enough for you to do all the problems. So let's look at this question, right? This question. Okay? Right? What is the first thing we do? First thing we do, we identify the load resistor. Well, they have made it easier. They have marked the load resistor in blue. Yeah? If it is not marked in blue, you pick the one at the extreme end, remove it, saying that's a load resistor. Right? I will also tell you how to choose this type of load resistor based on different problems later. Right now, what we want to do is to know how this analysis thing works. So here, please redraw the circuit as many instances as you want to solve the problem. Right? This is where most of you make a mistake. Redraw the circuit. We give you papers if you ask at an examination. We don't say, how many papers did you do? 2. No more paper. We don't say that. Use any amount of papers, redraw the circuit as much as you want. So here, I will take my circuit and I will redraw it like this. This is A and that is P. Right? This is E. It is 20 volts. R1. That is 5 ohms, R2, that is 5 ohms, this is 5 ohms, that's my circuit. Threw away the load resistance. Now, what is the first thing? Let's say we want to find out the question says, asks you to find the Thevenin equivalent, which means what? Voltage source and a series resistance. Series resistance is R of TH. Series resistance that you're going to find is R of TH. How do I find R of TH? One way is eliminate all the sources by replacing them with their internal impedance. So I will do that. Here I am throwing away this one. What would I do? It's a voltage source. I have to apply a short circuit if I want to throw away it and replace it with their internal impedance. So I have to draw a short circuit there. 1 resistor, 2 resistor, and that's my resistor. This is R1, this is R2, this is R3, and I look in through this to find RTH. Now, can you do this? Sure. R1 falls in parallel with R2. Yeah? You're not going to go R. It's all seen. Plus R3. So this is nothing other than R1 parallel to R2 plus R3. If you do not see this, then this point is this point. I can redraw the circuit. If I redraw the circuit, that's what I am going to get. Right? This is R3, this is R2, that is R1. Isn't this same? If you did not see it, redraw it. Don't worry about it. Right? I will look at then redraw it, I will look at final answer, you got it correct. So R1 in parallel with R2,
plus R3 is the RTH. Now we got to find the open circuit voltage. Right? We want to find the open circuit voltage. So let's take this to the other side. Here, right? Open circuit voltage, right? Did I say it's open circuit voltage? Oh, okay, I didn't. Nobody wondered what's going on. This VTH is nothing other than the open circuit voltage. This current is nothing other than the short circuit current, and RTH is VOC over IOC. Right? So you now begin to understand why we went and analyzed the source transformation. So what is open circuit voltage for this? So which means VAB when this portion is open. So when this portion is open, that particular resistor is useless, because why? It is hanging there. No current is going to flow through that. Right? So what would be the open circuit voltage? Can you give me a number? What is open circuit voltage? Yes? Huh? It's 10. If you did not see this, this is useless. So this particular current that is flowing through this is going to flow through this resistor, flow through that resistor. It's not going here. Both these particular resistors are going to have the same current flow through them. I can use what? The voltage divider rule. Right? So VOC is nothing other than 20 times 5, and that is 10 volts. So what it says is that this network is equivalent to a R of TH. What is R of TH? What is R1 parallel to R2? R1 parallel to R2 is 2.5, right? 2.5 plus 2 is, this is going to be 7.5 ohms, right? They are saying this is nothing other than 7.5 ohms with a voltage of 10 volts that will be connected across this resistance R. Right? That's what it says. This is A, this is B. That's what it says. This whole network basically onto the left hand side of AB can be replaced with a single resistor. Now I can calculate anything I want. What do they want after that? Find the. Now for R 2 ohms and 100 ohms, what would be the power? So if R is equal to 2 ohms, right? If R is equal to 2 ohms, we immediately know capital I is equal to what? 10 volts over 7.5 plus 2, right? Which is approximately 1 ampere. So we have P of R being I squared R, which is 1 squared times 2, it's equal to 2 volts. There you are. If R is equal to 100, right, then we know that I is equal to 10 volts over 7.5 plus 100, which should be approximately equal to 0.1 ampere, because why? 7.5 is very small compared to 100, right? So I can remove that, so this becomes 0.1 approximately, and then you have PR to be equal to 0.1 squared times 100, which is 1 watt. There you go. Right? Now we can make it more complicated by putting more sources and more resistors and all that stuff, but the actual technique of calculating is still this. Right? It's still this. Are you okay? Now,
you are going to be okay with this. Right? I have 2 more problems in the same area. I would want to do that. 9, 12 and okay, I will do 9, 12 in a little while. But I want to ask you, in your advanced level, if you had a system like this, if you have a system like this with a voltage source and a resistor and an unknown resistor, what should be the unknown resistor R value if maximum power has to be transferred? You have not heard of maximum power transfer technique. No. That's how they build antennas, right? If the antenna is a mismatch, maximum signal power is not transferred. Anyway, the antenna is your antenna that you have up there, the TV antenna, it doesn't have the basic signal that is picked up by the antenna is very small. So if there is a mismatch, that signal gets lost and you can't see the TV. So they have to choose. That's why when you ask when you go home, they say that you have to get a cable of impedance what? Have you heard of that? When you go to the store, you never go to the store, right? The store brings the TV to you, connects it, and you have no idea. But when we were kids, we had to go to the store, and they said get a 75 ohm cable. You guys need to now look into this because you guys are engineers. Remember, as an engineer, everywhere I go to, my aunts and uncles, any broken equipment, they think I am a wizard with a screwdriver who comes and fixes it. Right? So you have to know some words to sort of, right, slither away from those. So if you go and say to your auntie, there's no 75 ohm cable, maybe I'll look at 300, maybe mesh analysis has to be applied. I'll look into it and you can go. So you need to know the words. Right? You apply a TV cable, they ask you to bring a 75 ohm cable. Those days, when we were kids, ancient times, they were black and white TVs. They had 300 ohm cable. 300 ohm cable, you know the cable. Big cable. Now we have a thin cable. Now there are no cables at all, right? You got pure TV and dialogue and all that, right? You go and say dialogue satellite, give me a 300 one, they actually say, why you have a cable? You know, it already comes with it. So remember, please make sure you go out and learn. For example, electricity, I don't know if somebody taught you the, I guess, wires that they use in the electricity, the cables, the shapes and sizes, gauges. Next year. In the meantime, we want to find out what is the maximum transfer that you can have in the system. So let's say, for example, you had a simple antenna with a resistance RS, and the antenna had a signal that is going to be generated as Vs, and you want to ensure from this antenna to your basically the TV receiver, you transfer the maximum amount of voltage, maximum signal power. So we will say that this is RL, which can be varied. You immediately know that capital I is equal to Vs over Rs plus RL, right? Rs plus RL. Now then you understand the signal power that is transmitted. Oh, God. Taking a long time is not my thing. When you go home, you have audio systems, right? At home, the things that give out music, yes, entertainment. When you get speakers to it, again, you folks, they don't ask anything, they bring it in a thing and then they give you this nice diagram, connect this blue dot to the blue dot, red dot to the red dot, and put this button, press loud music. Then only thing you have used in these audio systems after that is the volume control. Just twist it up, twist it down. When the mom screams, bring it down. When she goes away, twist it up. Is that what you have done? Yeah? Yes. Rest of it we don't know. The speakers that come with it have some impedance. What is this particular impedance type? Yes, anybody who is a sort of some audio person like Bob? Yes. What is it? What is it? Most speakers these days come with an impedance of how much? 4 ohms. They say that the speaker is 4 ohms. So you can't just go to the let's say, of course, that's the reason why people send their audio sets with the speakers. When we were kids, we didn't have audio sets with speakers. We had to go and buy the amplifier separately, the tuner separately, and the speakers. Versus, of course, the speakers were like this tall, and when the bass comes up, you go. Right? Nowadays, there are 5 little pieces that are hidden somewhere. Right? So when you go there, if you go, when like an idiot and say, give me that speaker, give me this, you bring it home, you can't hear it. It will like that, what is this guy on the road, basically the lottery guy, right? And also go home and look at if you have some very, very expensive, high quality entertainment system on the speaker at the backside of the speaker, gold as backside of the speaker also. Go there and look at, there is a chart which says what the frequency spectrum is. What is the frequency spectrum that you can hear? From 2 up to 22 kHz. It has more than that. So even your dog goes, that's a high quality speaker. So if you have a high quality speaker with a certain ohm amount, and then on the other side you have a set that says 8 ohms have to be connected, you just bring any wire and hook it up. Not only the dog, even you can't hear what's going on. Right? So you have to pay attention to these things because those are the ones that engineers are supposed to. Now remember, you folks, you did your A-levels and failed. Did not touch electronics, did you? No. Soldering iron, unheard of. What is the soldering iron? You have here iron to the soldering iron you have not heard. When we came to engineering school, we kids, engineering school, I had my own radio. Of course, occasionally there were fireworks, but this is my radio. I made it. So you have to, the sound was awful, but we are happy. My radio. I tuned it, I got the speakers, I connected it, soldered it, I had equalizers. You guys have not heard of equalizers. Now the speakers saying, like the disco and screaming and all kinds of stuff, you have to put it and those things were equalizers. So we made equalizers. So when I came into engineering, I was partially an engineer. You folks, amplifier means above. Make them at home, right? Wait. Please don't make them at home. I'll have a lawsuit on my hands that he said so. Right. So here, this PRL is I squared times RL, and that's going to be equal to Vs squared times RL over Rs plus RL squared. Right? Look at this equation. In this equation, Vs is fixed, and RL is changing, and Rs is fixed. I need to find out what value should I put into RL. Sorry, what should I choose for RL so that the PRL is maximized? How do you do this? What mathematical construct am I going to use to find out how to maximize P when I change RL? If I have a graph, if I draw a graph of P, if I draw a graph of RL, PRL, what is the shape you are going to see here? What is the shape you are going to see here? This is a quadratic form. What shape does a quadratic form take? Like if y equals x to the power 2, what shape does it take? This way, right? Y is equal to like 1 over x square. Now those things you need to know.
This is going to take that shape. In fact, it's going to be a little bit of a lopsided shape, but generally this is the shape it's going to take. And there is a peak, and that is the RL star that you are looking to find the maximum power.
If I give you the equation of the graph, how can I find this maximum value? Yes? How? Huh? Anyone? Derivative, the first derivative of y against x is going to give you this. So dp RL over DRL, when that turns to 0, is this maximum point. So tell me, what is it? Take dp RL over DRL. Go, do, quick. You all of you are on the mathematics stream, right? In the advanced level. Right. Just hit it. So what is this construct form? V over U, right? Yeah, so d of V over U is what? V du minus U dV over V square. You give a notice, right? Yes. You go seem to know the differentiation. Right. Can somebody tell me the value? Maybe I should give you more than 3 hours for examination from the looks of this. 2-hour examination is not up your alley, I think, right, at this speed. Nobody got the answer yet. Yeah, what's it? Absolutely, 1%. Thank you. RL should be equal to RS. Right? Of course, I'm not going to do this. Right? But the answer is RL equals to RS. Right? You do this, and when you put it to 0, you get an answer which says RL is equal to RS. Right? So you realize when this impedance matches that, that's when you have the maximum transfer of power. This is the reason why I told you when you do your experiments, the equipment says you have a 50 ohm output, and all your cables at the other side also have to be 50 ohms if you want to make sure that your signals are in fact retained. Okay. Okay. That's okay. That's done. Now let's go back and do some other. So this is called the. This whole exercise that we did is called maximum power transfer theorem. I think
There is an experiment on this also. Changing R value and drawing this graph and seeing actually that you get the maximum value when the RL equals to RS. What is... Okay, here, this is a good question. Of course, all of them are good questions, but this is exceptionally good question. Only problem is I can't locate it. Okay, let me draw it up and then okay, so let's look at, I'll tell you what, let's stop there, right? Usually I do one problem each time, so I'm going to stop here. Today we have learned two most important circuit analysis methods, which will relax until I say so. You can't put away your books, because I might come up and say something else and you write it down. I have brought you two very important techniques. One is called superposition, second one is called technique. Those are the techniques that you are going to use to make sure that your circuitry becomes easy to analyze. Not a very difficult mesh and model type of analysis. Now, in fact, what I am going to do next week is half the class I am going to work out two problems that I think are important, and spend my time with two other problems that are proposed by the class. Now, when you come up with the questions that you're going to propose, I want to see the person who is proposing getting stuck somewhere, so that I have to actually do that in the class. Then DC analysis is over. We start AC analysis from next week. In the middle, I will talk a little bit about dependent sources. Maybe about 45 minutes about dependent sources. And you are going to realize all these analysis techniques that I have used are directly applicable to those sources as well, but with slight modifications. Right? Slight modifications. So, be prepared, be very ready, because your midterm, which is going to come in 2 weeks. Yes? Okay, which week is this? Where's the rest of it? Yes, which week is this? 4th week. So 2 weeks. So with the 6th week. This whole course is 12 weeks. So please, if you are stuck with anything, or if you need any questions answered, you need to indicate to them, you need to indicate to me right now. Right? Don't come and tell me I did not give you a maid repeat. I am a guy who never gives you repeats. No repeat. Come back next year. There's a repeat next year. Yeah. No repeats. Right? Because we are going to accreditation. We want to be recognized as engineers. We are 1/4 of an engineer right now, but we want to be recognized as engineers. So if we make it, we do not want to make it easy for you to jump from this level to the next year. We don't. Right? Because why? We want even a handful of people who pass out from SLIT to be called proudly SLIT graduates. Right? Not SLIT graduates. That's what we want. And to do that, I can't do it. Right? How can I answer all your questions? You are sitting in the desk answering them. So you have to make sure that you learn these things. Please do not send me. I know I told that in the previous lecture, somebody who sent me, I think I told you, right? Whole page was sent to me, no questions.
I'm not going to answer all those questions, okay? I want to see your handwriting, you get stuck somewhere and you write a little circle, say, I don't know how to do this, then take a picture and then send it. Right? Then, if I think it's worthwhile, I will answer in the class. If not, I will answer it and send it back to you. If the question is not too hard, I will answer that question and send it back to you. But if I think there is some important aspect that I want to teach in the class, I will do that question in the class. So it's up to you. I'll be doing 2, and I'll be spending a little bit of time in doing an additional 2 that comes from the class. All the other questions I will answer back to you individually, and you are free to put it on Facebook so that others are able to see. Thanks. Please wait, don't go anywhere. There's some stuff that people are waiting on that to give you.